Okay, the next part of the project is to determine the pile capacities. I'm going to show you an example, and then you can do the next part of the project using this example as a guide. So this is to find the capacity of the pile shown at both t equals 0 plus and t equals infinity. And of course, what does that mean? That means that for this silt, I need to worry about drained and undrained strength in that material, whereas for the gravel and the sand, I don't, because we're only concerned about the drain strength in the gravel and the sand. So the properties of the soil that we're most concerned about are given in this section here. And we may or may not need to use this part, but the pile is considered to be 1.5 foot by 1.5 foot, and it goes from 0 to 30 feet. So the tip is in the sand. You can see the tip of the pile is in the sand right there. The side shear is in the gravel and the silt. We have the water table there. So the depths that we're interested in then are what? Well, we've got 0, we've got 8 feet, and we've got 30 feet that we're concerned about. And of course I have to do 8 minus and 8 plus, because that is where the layer changes from the gravel to the silt. It's pretty straightforward, so I'm going to show you how to fill out. I'm going to give you a table similar to this. So what do we have to do at these depths? I have to come up with the sigma v, the u, and the sigma v prime. So you can all do that. So I'm not going to go through that part of it. Now, how do I get my sigma h prime? Well, I'm going to use the property here, which is the k. This k is meant to be the horizontal stress coefficient that we get after the pile has been installed. So after the pile has been driven or pushed or however it's gotten into place. So for the gravel, it's 0.8. For the silt, it's 0.75. So I simply take, for the gravel, it's 0.8. For the silt, it's 0.75. So I simply multiply these sigma v primes by those k values, and I get my sigma h primes. And of course, the top one is 0. Then I want to get my tau ff at t equals 0 plus. And then I need to get my tau ff at t equals infinity. So again, I have the same depths, 0, 8 minus 8 plus 30, 0, 8 minus 8 plus 30. Now, so the top layer of gravel, so let's start with the top layer of gravel there. And what the properties that what I need to use, of course, is the friction angle. But the friction angle in the gravel is 28 degrees, but because the pile is smooth, that the actual friction against soil to pile, gravel to pile, is going to be 0.8 times that. So I'm giving you this 0.8 here, and that gives me my delta. So what I get for my tau ff in the gravel then is going to be the tangent of 0.8 times phi prime. So it's going to be the tangent of 0.8 times 28 degrees. And then I take my 672, which is the sigma h prime, put it there, and I get my tau ff in the gravel there. at the bottom of the gravel, and it's 0 at the top because we have our sigma h prime of 0. So, and of course, since it's gravel at t equals 0 plus and t equals infinity, it's the same. No change there. So then to get the tau ff for the silt, now I have to use, because it's t equals 0 plus, I have to use the undrained strengths, and so I'm going to use my sigma v prime 840 and 1601, so those go here, and that sigma v prime is my sigma prime I. So I have my SU over sigma prime I, SU being undrained shear strength, and the ratio of those two is 0.35, and so the 0.35 is going to go there, and the 840 there, and so I'm taking, I'm using that ratio, but then I also have to take into account the fact that due to disturbance and such, when we insert the pile, that the strengths are reduced by an alpha factor of 0.8. So the strength is going to be the 0.35 times 0.8 times the sigma h prime. Or sorry, not sigma h prime, the sigma v prime. So we get 235 for this one, and again for this one it's going to be 0.35 times 0.8 times the 1601, the sigma v prime. So that gives us our tau ff at t equals 0 plus. For t equals infinity, then what do I have to do? I have to use the drain strength parameters, which are C prime and phi prime for the silt. And if you remember the equation, it is C prime plus sigma prime tangent phi prime. So, C prime plus sigma prime tangent phi prime, that's the base equation that we're using for the strength, for the drain strength. But then, of course, because the pile is driven in that, we have some factors that we have to take into account. Well, the C prime is 300, and the phi prime in the clay is 30 degrees. So the basis and the sigma prime is sigma h prime. So I take the sigma h prime there. This is my C prime, and so the basic parts of the equation are there. Then I have these two factors that I need to include because of the pile being driven, and where do those come from? The 0.7 and the 0.8. Well, they come from here. So the first thing is that because we've driven the pile, we have a phi prime remolded. In other words, we've damaged or remolded the silt by driving that pile. We've remolded the silt around the pile. So instead of the regular phi prime, it's reduced to 0.7 phi prime. And then again, because the pile is smooth, I have a delta which gives me a 0.8. So I have to use both of these factors, 0.7 and 0.8, to get the friction angle we're going to use. So it's 300, which is the C prime. I guess if I didn't point that out here, the C prime is 300 for the silt. And so we have 300 plus the 630, which comes down from here, tangent of 0.7 times 0.8 times 30 degrees gives me 490. And for this one, it's going to be 300 plus the 1030 times the tangent of 0.7 times 0.8 times 30 degrees, which gives me 611. So I get all the tau FFs here for t equals 0 plus t equals infinity. I'm now going to plot them. Here's my pile here, and so I'm going to plot the t equals 0 plus here, and I'm going to plot the t equals infinity here situation. So it looks like a Christmas tree, you can see, simply because we're going to plot it on both sides. So I start out at 0, so that 0 is there, the 277 is there, the 235 is here, and the 448 is here. And we show it on both sides because it's 448 there, 448 somewhere. So, and in reality, of course, I can't show it, but coming out of the screen here, I have the same thing. It's a square pile, so it has 4 of these things. I've shown 2 of them, 1, 2, but there are 4 of them, 1 coming out of the screen, 1 going into the screen also, so there are 4 of those. And then similarly, I have the 0 here. I've got the 277 here, the 490 here, and the 611 here. And that gives us the tau FFs for both situations. So then what do I need to do? I've got to find the areas of these. So I take the area 1, area 2, area 3. You can all do that. It's either a rectangle or a triangle. Area 1 is here, area 2 is there, area 3 is there. And similarly, I have 1, 2, and 3. I get the areas of those rectangles and triangles. Area 1 stays the same. Area 2 is this rectangle here. And area 3 is that triangle there. So you can all get those areas, and then we add up all those areas, and then what do? We need to find the volume. Okay, so we got the areas, but I got to find the volume of the stress block. It's a stress block, and I can't really show the 3-dimension, but I have a third, into the screen here. What is the distance? Well, the distance is, this pile is 1.5 feet by 1.5 feet. So it's a square pile. So in plan view, it looks like that at 1.5 feet. And this is also 1.5 feet. So that means that perpendicular to the screen, it's 1.5 feet. So I have to multiply that to get the volume of this. This is really a 3-dimensional image. So I have to multiply by 1.5 feet. So my total is 8621. I have to multiply. And then, as I said, we have 4 of those. So to get the total volume all the way around this pile, I have to multiply that by 4. So it's 4 times 1.5 times the 8621, and it's 4 times 1.5 times the 1320. And that gives me the side friction resistance, and that's 51,730 pounds, or 51.7 kips, 79,310 pounds, or 79.3 kips. So that is my Q side, the side resistance. Okay, so then we have to do the tip resistance. Well, like we said, the tip resistance, the tip is in sand, or gravel. Or what is it? It's sand, yeah. The tip is in sand. And so I'm now because there's the tip right there. So I'm now going to pay attention to, my layer 3, and I've got a friction angle of 34 degrees there. And because the pile does not go into the sand, I don't have to use all these reduction factors here and such. So, because it doesn't go down into the sand, it stops at the top of the sand, basically. And so I have my t equals 0 plus and t equals infinity tip resistance, but the tip resistance is in the sand, so these two are the same. So they're the same. Why? Because it's sand, and we're only interested in the drain strength in the sand. So for the sand, I have C prime is 0, so that's 0, which means I don't need NC star. So I'm only interested in the Q and Q star. And what is my Q? My Q is what? Is my sigma V prime at the tip, which is 30 feet. So that's 1601. And then how do I get my NQ star? Well, my friction angle, as we said, is 34 degrees. So that means that when I go into my chart here, this is my NQ star line right there. So I come in here at 34 degrees in here, and it's about 110. It's approximate. I read off about 110. So then I put my NQ star at 110. I simply take Q times NQ star, gives me 176,100. What is my Q tip? Well, now I'm looking at the plan view area, which is 1.5 feet by 1.5 feet. So it's 1.5 squared is the area, because that's the tip area. So 1.5 squared times the 176,100 gives me 396,200 pounds, which is 396.2 kips. And I want you to compute the pile weight. We're not going to use it for this, but later we might use it. The pile weight is what the volume of the concrete of the pile is 1.5 squared times 30 feet times 150 pounds per cubic foot. Gives me 10,125 pounds, which is 10.12 kips. But my Q ultimate at t equals 0 plus, what do? I add up the two numbers. So I take this 51.7, I take the 396.2, I add them together, I get 447.9 kips. That's for the t equals 0 plus. And then for the t equals infinity, I add up 79.3, 396.2, and I get 475.5 kips. So that gives me the pile capacities under this particular situation where the pile goes down that far. But what I want you to do is to do this particular case. This is your assignment. And here the pile goes down to 46 feet. So I've already done some of the work for you, but all this stuff is still the same. And but now you just need to fill out this particular table, and now we have the depths, these depths, which are, basically I've got 0 to 8, 30, 38, 46. 0, 8, 30, 38, 46. Well, why is it those? Because I've got 0, 8, 30, 38, 46. And then at every boundary, so here I have to have 8 minus 8 plus, 30 minus 30 plus, 38 minus 38 plus. So all of those depths are given here for you to work with. And again, I have the t equals 0 plus situation. I have the t equals infinity situation. You can plot them on this pile here, get the areas, the volumes, and that's going to give you your QS under the two different situations. And then now you have the tip resistance. Now the tip resistance is what? Now you have to pay attention to now we're in this gravel here, which is layer 5. So now you're going to be using these properties down here. To get that. And then, so we get our Qtip, and we add the Qtip and the Q side, and we get the Q ultimates down here. Now, this is for the situation where you're basically installing the pile without applying any fill on it. So another complication that we may add on would be, what is the pile capacity after, our surcharge has been sitting there for 5 years or for 20 years? Then the situation has changed. But for now, I just want you to do this part. Okay.